In this video, I will discuss how you can use Newton's second law and work with graphs. So we know Newton's second law says the net force is equal to the rate of change of momentum over with respect to time, and we know that momentum for relatively small speeds is mass times velocity. Now we can combine the two and prove that the net force is equal to the mass times the rate of change of velocity. So we have delta P, where P equals mv, can become mass times the change in velocity, and this is over the change in time. Now, don't forget, delta V over delta t, the rate of change of velocity with respect to time, is the same as the acceleration. So anytime you see delta V over delta t, you can try to remember that this is the same as the acceleration. So the net force then becomes approximately the mass times the acceleration. Now remember, this is not always true. This is true only in classical physics for speeds much smaller than the speed of light. Okay. Now, let's say we have the graph of momentum, the x component of momentum as a function of time. Let's say we have a relatively simple graph. This is the momentum of x as a function of time. Now, if you have this graph, how can you find the force graph? So, for example, how can we get the graph for the force? So this is time, and this will be the x component of the net force. So we have to use this graph and look at the expression here. This Newton's second law is telling us that the rate of change of momentum with respect to time will give us the net force. Now, this is the same as saying for the graph, the slope of this graph, the slope of the momentum time graph, will give us the net force. And from zero, from time equals zero to this moment in time, we have a positive slope, so we have a positive net force. Now, from this moment in time all the way to the end, the slope of this line is zero, so then the force drops to zero, and we have a zero fx x component of the net force. So finding the slope of momentum versus time will give you the net force. Now, we can do something similar if you have the Vx graph as a function of time, the velocity graph as a function of time. And let's say we have a velocity graph that looks like this, and I will use a different color. So I have a velocity graph that looks like this. Now, instead of using this expression, I need to see what's the relationship between the net force and velocity. So I have to move here. The net force is equal to the mass times delta V over delta t, the rate of change of velocity with respect to time. Now, in terms of graphs, this is just the slope of the velocity time graph. So the net force depends again on the slope of velocity versus time. So if I want to draw the graph of force as a function of time, then I just need to look at the slope. From this moment to this moment, I have a zero slope, so my force will end up being at zero. And then from this moment to this moment, the slope of the velocity graph is negative, so I know that my force will end up being a constant negative number because this is a constant negative slope. Remember, the mass is always a positive number. Remember that the mass is always positive. This means whatever the direction of the net force, delta V is going to point in the same direction. Whatever the sign of the slope is, the net force will have the same sign. Negative slope here, you will have a negative force on the force time graph. So this graph will give me this force, this graph will give me this force.